Invited speaker for this session is Gabe Epstein, and he's going to be talking about multidisciplinary methods for quantifying and tracking volatile migration and storage on tectonic scales. We'll give you the 5-minute wave.
Okay. Thank you to the conveners, and doesn't say it here, I am also a product of the GeoPRISMS initiative. My working group was called EFIRE, and we looked at exhumed rock record for volatile cycling and subduction zones in the Western Alps, almost none of which I'm going to be talking about today. So the insights that I'll be discussing are thermodynamic modeling, constraining slab inputs and thermodynamic modeling, and how that is important for volatile cycling. And it's a good follow-up to the last talk by Samir, because we have a lot of the same problems, and you'll see some repetition with different viewpoints, and I think that shows that already is ripe for collaboration. So the rationale of studying this from the slab or metamorphic perspective is that, roughly the majority of the cycled volatiles at volcanic arcs are ultimately derived from the subducted components. So it's super important to thoroughly understand what type of inputs and fractionations and other effects are occurring in the slab and transiting the mantle wedge. Fluid rock interactions in the slab, both at the seafloor and at depth, are thought to control redox and chemical transitions off the slab. And so this has broad implications on the largest scale for crust, atmosphere, and mantle processes through time and space. So I'm really going to break this up into some discussion of inputs. I think there'll be some nice overlap with the geophysical community, methods for quantifying devolatilization, specifically some of these advances in thermodynamic modeling we've had in the last 2 years, particularly in dealing with solutes in fluids being derived from the slab, and how that might be significant or contribute to some of the cycling. And then look at a couple ways to use these thermodynamic models to asymptotically approach open system behavior. Thermodynamic models are inherently closed system reversible reaction phenomena, but by making our batch calculations smaller and smaller, we can approach this open system behavior. And then touch on many of or a few of the many open questions. This is really a quick breeze through, and there's lots of more research that I won't be able to touch on today. So starting with inputs, it's very important to constrain your inputs into subduction zones, as Terry pointed out and others have in this workshop. There's extreme variability, heterogeneity in what's being subducted globally, regionally within a single margin, and vertically within a sediment or altered oceanic crustal section. So particularly when you're thinking about using subducted components as tracers, you need to quantify this quite well. So here, for example, at Hikurangi, on the far left, you have weight percent carbonate, the carbonate to total carbon ratio, and then all of the kind of isotope systems that we might use as tracers through this sediment section drilled by IODP 375. So this heterogeneity is evident at most of the margins, or all the margins that we've looked at closely. If you look at sediment input, so on the far left is some soon to be released for, for the illusion, showing this really along strike heterogeneity in sediment input. Similar studies have looked at Sunda And I did a little bit of work looking at Hikurangi, but never got around to going into too much depth. The reason for that is because we have heterogeneity in the volatile load, in the thickness of sediments, but you also need to understand and study closely from margin to margin basis what's happening to these sediments in the near surface. So for Hikurangi, for example, you have almost wholesale removal of the upper terrigenous trench fill sediments. And so they become almost obsolete in modeling, with the caveat that as you build this accretionary prism, you can transition to a erosional phase where you're actually re-entraining that material for later consumption in the subarc depth and contribution of that material to the arc gases. So just a close consideration of kind of the margin dynamics. Altered oceanic crust is another reservoir of volatiles that needs to be looked at carefully on a margin by margin basis. Some recent kind of synoptic work by Lee and others looked at alteration intensity in altered oceanic crust as a function of age, and found that looking at big delta of carbon species in the altered oceanic crust, that the precipitation of that carbonate occurs below 100 degrees C, and so you can correlate based on age and the retreat of the 100-degree isotherm in with depth. You can come up with some baselines of how altered your oceanic crust is and what type of volatile contribution that may have. With the caveat that if you're using this as a tracer of volatiles, particularly delta 13 carbon is all over the map on 20 per mil variation in terms of its carbon content, and so can make digging into carbon isotopes and volcanic gas is a little more tricky because you don't actually know what the initial values were. Serpentinates we heard a lot about in the last talk. And from a metamorphic perspective, this is a big concern as well. Again, in terms of delta 13 carbon of the carbonate in the serpentinates, you run this really large range, and we don't even know where serpentinization is mostly occurring. So there's plenty of evidence for abyssal serpentinization at Mid-Atlantic Ridge, for example, in these oceanic core complexes. And then some modeling by Ficenda and others, which supports some of the geophysical observations in a big way, that during slab bending, you get these sublithospheric pressure gradients or even negative pressure gradients with depth. So the slab, as Terry alluded to in her talks, is literally sucking water out of the forearc into these serpentinite zones. So careful consideration of what your inputs are is always warranted. Methods for quantifying this devolatilization. This is, so you need some knowledge of the pressure temperature regime. So you have some thermal model for a subduction zone. Shown at the top is Alaska and Honshu, kind of Honshu being a relatively cold subduction zone, or the and then extract from this your pressure temperature path to model the metamorphic reactions and devolatilization trends. So on the bottom left is the PT paths of the slab surface from the Syracuse fixed mantle decoupling depth model. So each of those represents a margin and the pressure temperature path that it goes, with the intersection with the convective mantle wedge being at 80 kilometers depth, where you have this massive swing in temperature, and therefore you're releasing volatiles. This is not the whole story. That's the slab surface story. But as you go to depth in the slab, you have refrigeration of that interior of the slab from the overlying material. So on the right, showing 3 margins, from Tonga being the coldest to Cascadia being the warmest at the subduction interface, and 7 kilometers beneath the interface. You have totally different pressure temperature pathways. and that has consequences for the CO2 release, in this case, from a altered oceanic crustal composition. So we use, I use Perplex, or other folks use similar thermodynamic modeling software to ascertain where we're having devolatilization. Perplex is a Gibbs free energy minimization software. I'm sure that people have heard about it. I'm not going to get too into the weeds on how it's done, except to say that it's closed system, reversible reactions, and given some, fictitious 3 mineral system, Perplex splits it up into grids. It analyzes every grid point for every possible combination of minerals and their solid solution end members to determine what the minimum Gibbs free energy of that system is. And then you form a pseudo section that, depending on your resolution, matches with the reality of the situation. These pseudo sections get really messy when you go to subduction zone pressure and temperature ranges. So this is a raw output from Perplex for a serpentinite with temperature on the x-axis and pressure on the y-axis. And the difficulty here is that as a metamorphic metrologist or a thermodynamicist, you have to go through each of these phases and make sure that it's a reasonable assemblage and a reasonable phase transition. And that's because Perplex auto picks these boundaries, whereas some of the other programs, the user inputs which reaction they're interested in. You will not see this in any volatile devolatilization body of work. What you will see, though, is the H2O, CO2, or other volatile content loss on this pressure temperature grid. And so just knowing what went into that and what is shown is an important part of the battle. So this is really what we distill the petrogenetic or the pseudo-section grids down to, is where are you going to have fluids released? And so here is for serpentinite, H2O in the middle, CO2 on the right, and for 2 different PT sections for Hikurangi in New Zealand, showing that you're preserving serpentinite until very deep in the subduction zone, around 6 gigapascals, and CO2 on the other hand is kind of released in more gradual amounts, but you have a very small amount of carbon dioxide to start. So advancements in Perplex. Fluids in Perplex have traditionally been treated as carbon, oxygen, hydrogen mixtures using various equations of state. I just have one listed there, kind of the most common one for how this works. So you have a H2O solvent, and you can dissolve methane, CO2, O2, H2, any kind of carbon and oxygen species into that. But non-volatile major elements are confined to the solid phases. So you're only looking at gas components dissolved in a fluid. Recent advances is the real kind of exciting recent advance for volatile cycling is the implementation of the deep earth water model into Perplex. The deep earth water model arose from, or I guess was planned the whole time, but in 2014, Sriensky and others released a paper expanding the calculation for the dielectric constant of water to these extremely larger range. And so that expanded on SUPCRIT, which was our original best estimate for solubility of electrolyte species in high pressure temperature environments, which was 5 kilobars. So this advancement from 2014 expanded that to 6 gigapascals at 1200 degrees C, and has been relatively rigorously, cross-checked with experiment for certain chemical systems. And so now, using Perplex, we can get electrolyte speciation and major element dissolution, though this is still being refined. This has led to some startling things, as Terry pointed out, particularly down here, you can see that in this model at 5 gigapascals and below about 850 degrees, you have acetate, acetic acid, these long, organic molecules that are super complex as the dominant carbon carrier, also a charged species. It doesn't get much better when you look at other species. So from 2019, they looked at eclogite metamorphism and fluids in equilibrium with that. And so on the left of these three figures is shown the experimental calibration, and the red line is the solubility determined from this model. And then on the right is the speciation you see in that. So for magnesium, you have this, bizarre silica, hydrated silica carbonate ion that is the main carrier. Aluminum, which is relatively mobile because it's merged with this hydrous aluminum silicate stuff, and then really complex distribution of silica in solution. I'm going to leave this here. I'm not going to get into this, but I think that this is a new pathway, and it really, once this gets refined a little better, we'll be able to determine the ionic activity of these fluids coming off the slab, which is potentially very important for the geophysical community and for the community interested in redox in these subduction zone settings. Okay, so taking a step back from getting in the weeds with Perplex and just looking at the historic and new implementation and devolatilization patterns we see in subduction zones. So there's two typical ways that devolatilization is modeled as we progress through subduction, and that's either approximating channelized flow or pervasive fluid flow. So given some prescribed lithologic stack, you initiate subduction. And so for this channelized flow model, where the fluid is unreactive after it's produced, so in starting at the bottom of the stack, you determine if a fluid is thermodynamically favorable. If it is, you extract it and you send it to the slab surface, and then you go to the next node up, and you do that all the way up the stack, and then you take that whole stack and you shift it down to greater depths to model the devolatilization throughout the subduction zone. The pervasive flow model, when you have a fluid produced at depth, you pass that fluid up into the next grid cell, you equilibrate it with the rock, and then you model the thermodynamics of that new bulk composition. So in some cases, particularly, for example, if you're passing from a serpentinite into a gabbro, you're going to lose your fluid, and it'll be stored till further depth because you have this relatively water poor gabbro. In other instances, you just have a cascade of more fluid production. And so these two models lead to different distributions of fluid at the surface or at the slab surface. But in reality, as with everything in geosciences, the in-slab flow regime is likely intermediate between these two. There's been some work 2015, 2014 by Flunder, showing that in serpentinites where you're away from high strain, you have initial pervasive flow, but then within meters of fluid production, you form fluid channels. And so there's strong evidence for, at least away from the subduction interface, you're looking at more of a channelized flow regime. As you approach the subduction interface, strain rates increase, material competency decreases, perhaps then it should be modeled as channelized flow. And nobody has modeled this as a changing gradient of fluid flow patterns, to my knowledge. Okay, so the first attempt at modeling this was that of Borman and others in 2006. And so the channelized flow model is on the top for cold slab devolatilization, and it shows this one major peak of CO2 and H2O flux together at 4 arc depths. this is a common occurrence in all of these models, is that the initial pulse seems to be coming out at the forearc, exception of Hikurangi because the slab depths beneath the arc are around 70 kilometers. When we do the pervasive flow model, which the third axis here, when coming out towards you, is how much hydration there is in the lithospheric mantle as serpentinite. You see that it's a much different distribution, and you have 2 points. Thank you. So you have this forearc pulse and this somewhat counterintuitively back arc pulse of fluid. Nothing really happening in the arc. But based on some of the great models of fluid flow, it's likely that or of mantle wedge flow and fluid constraining in there, you probably are getting some of that material into the subarc region. So this model is kind of the extreme case, 20 kilometers of mantle hydration, pervasive flow. The CO2 return efficiency globally from this model was 15 to 100%. Significant forearc and back arc loss, and perhaps some mantle metasomatism as a significant volatile reservoir. This was using the classic COH fluid equation of state without the Dew model. So looking at a margin specific study, this is some work that we did at Hikurangi in New Zealand, and looking from north to south, you have this slight increase in the thermal conditions of the model. So you have some variation in the temperature, and then we also look at variation in the crustal structure. And what with Davy and Mochizuki models being derived from geophysical interpretation of the crustal structure. So this allows for better constraint of where fluids are being produced and how much, but it also highlights the importance of the incoming lithology on the distribution and volume of fluids being produced. So the black line here is the North Island of New Zealand. The red and white points are sample points from this study from us and Gegenbach. And you see the distribution of H2O, a shallow forearc pulse, a subarc pulse, and then this back arc pulse from serpentinization. This was a channelized fluid model, so no fluid rock interaction once the fluids were produced. And then a single CO2 pulse. If we look at the models derived from geophysics for the crustal structure, though, you have a much different distribution of CO2 and water, where you have just this broad blanketing of CO2 with a peak at the subarc range and going back. All in all, this study showed about 60% of the CO2 is removed from the slab. 36% of the total CO2 in the slab is coming out at subarc depths. And most of that is being derived from altered basalt. And so this is something else you can do with this kind of stuff. So here we have depth to the interface, increasing from right to left. The CO2 production off of the slab as the black line, and then the contribution from the various subducted elements to that CO2. And you can see that you have a pulse of sediment-derived CO2, then after that, it becomes a altered oceanic crustal contribution dominantly. And the normal crust is on the left, double crust is on the right, and you can really see the effect of having a thickened crustal component leading to refrigeration of those lower units, which seems to be important. Perplex does not model trace elements. So to do so, you have to get a little creative. In some cases, you can look at major element transitions or major mineral breakdowns and correlate that with what trace element should be released. Or you can just relate with the Dew model, major element released to the fluid and correlate that with minor elements. So for example, assuming you have a linear correlation between nitrogen and potassium content in the rock, you can look at potassium release and correlate that with nitrogen release from the slab. And you see a much different distribution of nitrogen than you did for CO2 coming off the slab. And in this case, we're looking at really really good preservation of nitrogen within the slab material, only about 10% loss from the during subduction. More recent work has really explored the deep earth water model in regards to subduction with hot, medium, and cold margins, and looked at other elements, aluminum, silicon, potassium coming off the slab. And you see again this two-peak model here. And this study really nicely binned subduction zones into three kind of volatile conditions. One being carbon limited, water limited, where you have more carbon left in the slab, and ones that are thermally frozen, where they're just trundling along with very little devolatilization. And there's our global distribution. So most of these models indicate fluid and volatile pulses at variable depths. Volatiles follow the water. Characterization of the inputs is important. The PT regime has a major control on the fluid release, and the volatile species need a lot more research. Open questions. I wanted to discuss sulfur briefly. There's been some really cool recent work using the GeoPRISMS model to look at sulfur loss from various rock types and speciation given a redox state of the fluid or the slab. So the pie charts here refer to the speciation of sulfur coming off the slab, which brings into question redox. There's some camps that argue for control of subduction zone redox, fluid redox conditions by serpentinization. On the left, Evans and others saying that the degree of seafloor serpentinization controls whether you have reduced or oxidized fluids coming out of that. Whereas Coley and all more recently saying that no, it's a matter of which minerals are dehydrating where, and that controls your redox budget. And then most recently, Agu and others saying doesn't matter what's happening in the slab. Once you get to the interface, you get the sediments, that's going to buffer everything. I don't think sediments are being subducted everywhere, so I don't know. Maybe there's some other method oxidizing the interface. But they showed that in these calculations, a relatively modest thickness of sediments, in the thickest case, 100 meters, is enough to fully buffer reduced fluids coming off the slab. I would be remiss if I didn't mention the metamorphic rock record and for our carbon loss. On the right is a model from Central America showing the significant for our carbon loss and sequestration in carbonate. But the metamorphic rock record is actually indicating that you can explain all of the isotopic compositions of carbonates through internal equilibration without the need for open system fluid or carbon loss. I will skip that, but it's potentially important. And lots of other outstanding questions. I have some that are, I think, are tractable, and some that are just much more open-ended. How is volatile transfer counted through the mantle wedge? And what, if any, are the storage reservoirs as we go from the slab to the crust? Thank you.
We probably could do one question or so. Anyone have a question? Michelle.
Hi, thanks for the talk. I'm really interested in deep earth water model. So I was wondering if you could speak a little bit to what extent this model works feature would affect geological interpretations, and also whether or not you need any additional data to resolve this quirks, or whether or not it's more a question of like addressing computational background.
Right. So the quirks, so those kind of atypical mechanisms of volatile transfer, those long chain electrolytes, I'm going to call them long chain, but those came out of the model and it matched well the solubility experiments that had been done. So it seems like potentially for that well-defined system, that actually may be what the speciation in the fluid is. And so it's a matter of our understanding from a non-experimental standpoint, what kind of ramifications that might have. And what was the other part of the question? I'm sorry.
I think you might have covered it already. I was curious, I guess, if they are, if some people do think they are spurious, or whether or not the model needs to be adjusted to tackle, natural conditions,
Right.
what types of adjustments might need to be made?
So the main adjustment is that you can't use the model outside of, well, you can't easily or safely use the model outside of things that have been experimentally determined. Because if you just toss this model in to perplex and model like a sediment or something, you get some super bizarre results and some ionic activities that trend towards infinite. So you have a fluid that is just unreasonable. And so it really needs to be done cautiously and carefully. And I think that hopefully that will be borne out in the coming years, but it's definitely in its infancy. And it's a tool that a lot of people are using without the care that it needs to be used.